S. Chan presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
So we all are surrounded by so many solids. There is diamond, sand, rubber, but have we ever wondered that all these solids, they have different textures, they have different rigidity. So what makes diamond so hard and what makes rubber so soft, although both are solids? So welcome to S. Chan Academy, myself Dr. Mamta Sethi. So today I will be discussing with you, more about solids, their properties and the structure of the solids. To study this particular topic in more details, you can refer to the book by S. Chan Publishing. The link to the ebook is given in the description box. Solids are, of course, as mentioned in the previous lectures also briefly, that the most ordered state of the matter. Now, what do we mean by most ordered state? It means that atoms or molecules or ions, these solids are composed of, they are arranged in a definite pattern. There is a definite shape of these solids, right? Solids have a definite shape. Now, these solids also, they can be divided into two categories. So, they are crystalline solids and amorphous solids. Some of the solids you must have observed, just like diamond, you must have observed that it is so hard and it has a definite shape, right? So it can be put in the category of crystalline solid. Now what is different about the amorphous solids from crystalline solids? These are the few points which I have highlighted in order to differentiate the two types of solids. Now crystalline solids, most ordered, means the atoms or molecules are arranged in a definite pattern and that pattern gets repeated over a long range. So they have a long range order, right? Even if we go to infinity, this particular structure will be repeated over and again. Whereas amorphous solids, there is no set pattern. Though they are solids, but it's better to call them, they are not truly solids, because atoms and molecules which are there in the amorphous solids are not arranged in a regular pattern. And even if this regular pattern persists, this is going to exist for a very short range. So short range order can be observed in amorphous solids. So they are like powdery kind of solids, not as crystalline as the crystalline solids are. Now, what is the difference between the melting points? We all know what is a melting point. So, when a solid is heated, so what happens that the atoms and molecules which are present at their respective positions, they start vibrating, and they start vibrating with more and more frequencies, and they vibrate so fast that they overcome the intermolecular forces and they leave their lattice position. It is exactly at that point a solid melts. So when a solid converts into a liquid at a particular temperature, the process is known as melting. And for crystalline solids, this change happens very sharply. Like when the solid starts melting and when the melting is over, the temperature remains same. So solids, crystalline solids, they have sharp melting point. Whereas amorphous solids, you must have seen glass. How does a glass melt? So if glass melts, it will not melt at one temperature. It will slowly and steadily softens and then start converting into the liquid state. Now this process of melting for amorphous solids does not happen at one single temperature, and hence we can say that amorphous solids do not have any sharp melting point. And also crystalline solids, they have definite shape, but amorphous solids, again owing to their irregular arrangement of atoms and molecules, do not have any definite shape. Now, so we have understood that the solid state is the most ordered state. Now, order is the result of symmetry. So, there is symmetry in the crystal. Symmetry is a very, very important property. Now, when we talk about the symmetry present in the solids or any other object or any other molecule, in a single molecule also, in fact, we talk about these three symmetry elements. So, we talk about what? Symmetry elements. So, I will discuss these symmetry elements one by one. Now, let us talk about center of symmetry. So, these symmetry elements are basically present in the molecules, So, suppose we have molecule called carbon dioxide, Now, at carbon, what is there? This is the center from where we move to either direction and we have the same kind of environment. We move to this direction, we move to this direction, the same kind of environment is seen on both sides. So, this is called a center of symmetry. Now, coming down to the line of symmetry. Now, what is a line of symmetry? A line of symmetry is basically a line about which a molecule or a solid, when rotates, it produces the same kind of arrangement or the same kind of appearance in a complete cycle of 360° more than once. Let us take a very simple example of water molecule and imagine that there is a line, this line, right, about which I would like to rotate this water molecule. Now, if I rotate water molecule about this axis, what will happen? When it is rotated through 180°, the hydrogen, let us for the sake of convenience label these hydrogen molecules, though we know that both are identical, but we can call it H1 and H2. Now, upon rotation by 180°, what will happen? Hydrogen 2 will come here and hydrogen 1 will go there. But the kind of arrangement we have is identical to what we had here because both the hydrogens are indistinguishable, right? So, we can say that in a complete cycle of 360°, water shows identical appearance twice. So, we can say that it has a C2 axis of symmetry. So, axis of symmetry can be defined as an axis or a line about which when a molecule is rotated, it appears, it shows identical arrangement more than once. So, how many times it is showing the identical arrangement? Here twice. So, 360° divided by 180°, the angle at which the molecule is rotated gives us 2, and therefore we can say that water molecule has C2 axis of symmetry. C stands for axis of symmetry, and then this subscript, in general we can write Cn axis of symmetry. So, this is C2 axis of symmetry. Now, depending upon the molecule, depending upon the solid which is under consideration, it may be C2 axis of symmetry, C3 axis of symmetry, C4 axis of symmetry, and we also called it this C2 axis of symmetry is also known as twofold axis of symmetry. Twofold axis of symmetry means in a complete cycle of 360, the water appears identical twice. So, twofold axis of symmetry. In, let's say, ammonia molecule, if it is there, ammonia we know that it is, pyramidal. So, what will happen? An axis which is passing through the nitrogen and the hydrogens are arranged in a pyramidal fashion. So, this is, let's say, the axis. About this axis, if you rotate the ammonia molecule by 120 degree, then identical arrangement of atoms will be observed. And therefore you can say that ammonia molecule has 360 divided by 120, what do we get? We get 3, so it has C3 axis of symmetry, which is also known as threefold axis of symmetry. Now here I have talked about the symmetry elements which are present in a molecule. For the sake of simplicity, we will be then considering these symmetry elements which are present in the cubes also. Now before that, let us understand what is a plane of symmetry. Now again, let us take the example of water molecule. Now instead of a line, we have a plane. So let's say this is a plane. Now plane of symmetry is a plane which divides the molecule into two identical halves. So one half is this side and one half is this side in such a way that the two halves are what? They are mirror images of each other. So if through this plane you are able to see the two hydrogens, you will be observing it yourself that the molecule gets divided into two identical halves. So this is called a plane of symmetry. Now since we are focusing today on solids, so let us now see that what symmetry elements are present in solids. Now there are a variety of solids, but I will take the example of the simplest solid, that is the solid which exists in cubic arrangement. Simple cubic solid, simple cubic crystalline solid I am taking the example of. Now the number of symmetry elements which are present in a cubic arrangement are 23. Let us understand now that how these elements of symmetry can be located in a cube. So first of all, let us understand the symmetry axes which are present in the cube. Now this is a cube, right? We all know that how a cube looks like. Now what do we understand by the axis of symmetry which is present in a cube? Now in this cube, the axis which passes exactly to the center of the top face and the bottom face, right? We have a cube and the axis which passes through the center of this face and coming out from this face. About this axis, what will happen? About this axis, if you try to rotate the cube, what will happen? You try to rotate. This edge will come over here, or we can say that this face, this particular face will come in the front. The one which is in the front will move towards the side and the one which is on the side will move at the back. So it means that about this axis, how much is the angle of rotation? If you rotate it through 90 degree, you will observe the identical arrangement. So what is the the order of the axis which is present over here? Again, to get the order, we divide this 360 by 90 degree. So we get what? 4. So what is the order of this axis? C4. So C4 axis of symmetry. 4-fold axis of symmetry is present. Now this is not the only C4 axis of symmetry which is present in the cube, because the identical faces are this face and this face also. So we've talked about the axis of symmetry which passes through the top and bottom face of the cube. The similar axis will be passing through the left and right face of the cube. A similar axis will be present which passes through the front and the back face of the cube. Therefore, in total, we will have 3 axes of symmetry, 3 four-fold axes of symmetry which are present in a cube. Now, in a cube or in any other solid, there may be one or more than one axis of symmetry which can be present. So, apart from fourfold axis of symmetry, there is also this axis which can be drawn from one corner of the one face to the other corner, right. So, the line joining this corner and this corner, if you rotate the cube along this axis via how much? Via 120 degree, you will find the identical arrangement of this cube. So, if you rotate it by 120, so that means 360 divided by 120, you will get 3. So, it means this axis is which? This is C3. So, threefold axis of symmetry. So, how many? Since we know that how many corners are there, so this axis is getting formed by joining the 2 corners. So, we all know that how many? 8 corners are there in a cube. So, 4 such axes can be drawn, and therefore we can say that 4 C3 axes of symmetry or threefold axes of symmetry are present in a cube. Then coming down to two-fold axes of symmetry. Now, two-fold axes of symmetry, how can you? So, for this you need a little imagination. You need to imagine the 3-dimensional structure of a cube. You can always take a Rubik's cube in your hand, and you can try visualizing these symmetry axes in a cube. It will be very easy for you to understand the concept. Now, taking the center of this edge which is present at the top face of the cube and the bottom face of the cube, a line joining these 2 points, see, center of the edge and center of this edge. So, center of the edges. So, this line particularly, about this line, if you try to rotate this cube, you will find that the identical arrangement of atoms will be observed, or the identical configuration of this cube will be observed how many times? Twice, only twice. If you rotate it by 180 degree, you will observe the identical arrangement. So, 360 divided by 180 degree, you will have 2. So, it means, what is the order of this axis? It is C2. So, two-fold axis of, this is called two-fold axis of symmetry. Now, this is not the only axis of symmetry which is present in the cube of this type of two-fold, right? So, how many edges are there in a cube? There are 12 edges which are present in a cube. So, obviously joining these edges, for example, if I join center of this edge and center of this edge, so one such axis can be generated. So, there are 12 edges. So, we will have 6 C2 axes of symmetry in a cube. So, in total we can say that how many axes of symmetry? 3 plus 4 plus 6. So, there are 13 axes of symmetry which are present in a cube. Then we come down to the center of symmetry. There is only, what is center of symmetry? So, it is exactly at the center. From this center you go to any direction, the distance is what? Same. So, this is called center of symmetry. There is only one center of symmetry which is present in the cube. So, coming down to the plane of symmetry. So, we know that plane of symmetry divides the molecule or the solid into 2 identical halves. So, we can see here also that if we take a plane Plane is what? So, this plane, I'm talking about this plane. So this is what, if you put a plate in between, right in the center in the cube, it will divide the cube into two identical halves. So this is called a rectangular plane of symmetry, right? Since it is formed by, cutting the faces through the center. So how many faces are there? There are 6 faces. So therefore, in total, there will be 3 rectangular planes. So one such plane will be perpendicular to this also, and the other plane will be like this, horizontal plane also. Then we have another type of plane, which is your diagonal plane of symmetry. Now diagonal plane of symmetry can be plotted. So one edge which is at the back, bottom face, front edge, joining these two, you can have this plane. So this is one plane like this, which divides the cube into two identical halves. But since this is formed by joining the diagonal of the cube, therefore it is called a diagonal plane. 3 such planes will exist in a cube. And again, there's another type of diagonal, right? You can also draw a diagonal like this, and joining these you will have what? This is another type of diagonal plane, and 3 such diagonal planes also exist in a cube. So 3 rectangular planes and 6 in all the diagonal planes. So 9 planes of symmetry exist in a cube. So this is all about symmetry elements which are present in a cube. Now you may be wondering that why am I discussing about these elements of symmetry in a molecule? What role do they play in deciding the geometry of a solid or the structure of a solid? To get the answer of this question, let us watch the next part of this video.
Hello everyone, I am Dr. Richa Arora and welcome to S. Chand Academy. So I am going to make videos on very important topics of physical chemistry. और topics होंगे solutions, phase equilibrium, conductance and electrochemistry. इन videos में हमारा focus रहेगा basics पे और applications पे. तो ये वीडियोस चाहे आप अंडर ग्रेजुएट स्टूडेंट हो, चाहे आप पोस्ट ग्रेजुएट स्टूडेंट हो, चाहे आप इंटरव्यू की प्रिपरेशन कर रहे हो या किसी एंट्रेंस की प्रिपरेशन कर रहे हो, ये सारी वीडियोस आपके बहुत काम आएंगी. सब्सक्राइब कीजिए एस चांद अकेडमी एंड प्रेस द बेल आइकन टू गेट द नोटिफिकेशंस.
So welcome back to S. Chand Academy. The question I asked you before the break was that why do we discuss about these symmetry elements, and what type of symmetry will we be having in crystals, in solid crystals. To understand more about the structure of the solid, let us first understand the 2 terms which are very, very important, that is your unit cell. So unit cell basically is the smallest entity, the smallest repeating unit, which of course will get repeated over and over again along all the 3 directions to give you a complete lattice. So the complete solid is not composed of one unit cell. This unit cell will get repeated. You all must have seen a wallpaper, where a definite pattern gets repeated over the entire area. What is the difference between a wallpaper and this 3-dimensional crystal lattice is that the wallpaper is simply 2-dimensional thing, and the space lattice which we are talking about is a 3-dimensional thing. So that means this unit cell is going to get repeated in x direction, in y direction and in z direction in order to get this complete lattice. So what is this? This is known as the space lattice. So as we can see that this particular portion is representing one unit cell. On repeating this unit cell in different direction, in all the 3 direction, what do we get? We get something which we call as the crystal lattice. Now in a crystal, let us understand that in a unit cell, these are 3 axes. So along x, y and z direction we define more. So we define small a, b and c, which are known as crystallographic axes. So these are the crystallographic axes. They may or may not lie along the x, y and z direction and between the two faces, right? So there are angles which are formed. These are called interfacial angle. So A, B and C, these are called crystallographic axis, and alpha, beta and gamma are called interfacial angles. So these are of course important in order to understand the structure of solid. Now let us see that these solids, depending, we have understood that solids have certain symmetry elements, solids have crystallographic axes, they have interfacial planes. Now depending upon how the crystallographic axes are related to each other, right, we can have different types of crystals. Now all crystals, all solids, they are not following the pattern as we have seen in the case of simple cubic. Some may be different. So in nature, nature has been kind, otherwise we would have had n number of structure of the solids and it would have been really impossible for a chemist or for a scientist to explain the structure of these solids. So nature has always been kind to us, so therefore it has decided, it has fixed the the kind of arrangement we see in these solids. So depending upon the type of arrangement, these atoms and molecules in a solid can have, these crystals are divided into 7 types, namely cubic, orthorhombic, trigonal, monoclinic, triclinic, tetragonal and hexagonal. And also there are 7 crystal types. So depending upon the kind of unit cell a crystal can have, there are 7 crystal types and 14 Brevis lattices. So these are the types of unit cells which are possible: simple, primitive, or simply we call it primitive, simple cubic also we call it. So what is simple cubic structure? Let's say we have a cube and the atoms are present at each corner of this cube. So this is called a simple cubic structure, right? So at all the 8 corners we have one atom. So these are called the lattice positions. Each position is occupied by atom or a molecule. Then next we have a body centered, which is represented by the symbol I. Now body centered is slightly different from simple cubic or primitive. Apart from the atoms at the corners, like all 8 corners are occupied by the atoms, apart from this there is one atom which is at the center, exactly at the center of this cube. So this forms the body centered cubic structure or unit cell. There is another type of unit cell which is called face centered. Now what do we mean by face centered structure? In face centered, in addition to the atoms at the corners, right, atoms at the corners, we do have atoms at the faces, like on each face we will have, right. So we will have right and left, top and bottom, and then we have front and back. So we will have 6 atoms, one on each face other than one on each corner. So this is called face centered cubic arrangement. So this is called BCC in short, this is called FCC in short. Apart from these three arrangements, there is one more arrangement which is called base centered, which can also be called as end centered, and this is slightly different from this is slightly different from face centered, as in apart from the atoms at the corner, there are atoms on the two opposite faces. Right? We have one at this face and one at this face. So this becomes your end centers. So these are basically four types of unit cells. So unit cells we have understood is the smallest entity. These are the four possible ways in which the atoms are arranged in the unit cell, and these unit cells are part of what? There are 7 crystal types. So these 7 crystal types, each crystal type can exist in all of these forms, or maybe one of these forms, 2 of these forms, right? So depending upon in how many forms these crystals can exist, there are 14 revised lattices in which the entire solids, all these solids which exist in nature, they can be divided into 14 revised lattices. Now after having understood this concept of revised lattices, there are few laws which governs the the solids. So there are few laws which are applicable to the crystals. So first of these laws is the law of constancy of interfacial angles, right? So what do we mean by? We know that what is an interfacial angle? The angle formed between any two faces of the crystal. Let us understand this is one face of a hexagonal lattice, hexagonal solid, right? So this is the angle, right? This is the angle which we know that it is 120 degree, right? Now this law of constancy of interfacial angle says that irrespective of the size or shape of the crystal, right? It can be slightly elongated also, it can be smaller in size also, and it can be big enough also. But the angle between the corresponding faces, the corresponding angles, right? We are talking about this interfacial angle. So irrespective of the size of the crystal, this angle remains same. So angle is 120 degree in all these crystals. So this is law of constancy of interfacial angle. So there's another law which again describes the properties of the solids, is law of rational indices. Now law of rational indices talks about the intercepts which the crystallographic planes makes on these crystallographic axes. So what do we see here? We see here these are the crystallographic axes. So A, B, C, which are lying along X, Y and Z direction. Now this is one plane. Let's say this is one crystallographic plane. Now what are the intercepts that this plane makes on these crystallographic axes? It has travelled or it has covered, let's say, A distance along X axis, B along Y axis and C along X axis. So the intercepts which this particular plane A, B, C makes on these crystallographic axes are A, B, C. Now this law of rational indices says that the intercepts made by any of the crystalline faces, right, on these crystallographic axes can be either ABC or integral multiples of ABC. Like this is another plane, right? KLM is the other plane, right? This is another crystallographic plane. Now what are the intercepts that this plane will make on these crystallographic axes? It will always be integral multiple of A, B and C. So having a close look at the intercept, so this distance, this particular distance OM is almost double the distance of OB. So therefore we can say that the intercepts which plane KLM makes on these axes are 2A, 2B and 2C. There is no concept of fractional intercepts, right? We cannot have. So it is the simple logic behind these is that atoms are placed at their respective lattice positions. There is no atom in between, right? So there is no concept of fractional. We cannot have intercept 1.5a. No, these intercepts will always be integral multiples of A, B and C. So there is another very important concept which gives us the information about the crystallographic planes which are present in a crystal. To define a particular plane, that which plane, the coordinates of a particular plane, they are described by these integers which are called as Miller indices. These Miller indices are denoted by HKN. So Miller indices of a face of a crystal are basically inversely proportional to the intercept. So just now in the previous slide we have understood about the intercepts made by a plane on the crystallographic axis. So those intercepts can be described in terms of Miller indices, which is again will define a particular plane. So let's say HKL plane, this is one plane. So how do we explain it in terms of Miller indices? So this particular plane which is highlighted in the pink shade, the coordinates of each point are given. So what are the intercept that this plane makes on the crystallographic axis are, let us first understand that what are the intercepts that it makes on X, Y, Z axis. So X, Y and Z. So the intercepts on X, Y and Z, what are the intercepts? So intercepts are, it makes, so the coordinates of this point are 0, 0, 1. So what is the value of C over here? It is 1. 0, 1, 0. B is 1. 1, 0, 0 along X axis, it has travelled A distance. So along X, it has travelled A, so intercepts A, so they are integral multiple of A, so we can also write as 1. So the intercept can be written as 1, it can be written as A also, but I am just writing the numerical coefficient. So this is also 1 and this is also 1, and then what you have to take? You have to take the reciprocal of this. So Miller indices are nothing but they are the reciprocals of the intercepts made by this particular plane on different crystallographic axes. So reciprocal, what is the reciprocal of 1? It is 1 only, right? So it remains 1. So what are the Miller indices of this particular plane? They are 1, 1, 1. So 1, 1 plane. In short, we write that this is 1, 1, 1 plane which is present in a crystal, right? So in this particular lecture, we have mainly focused upon the general arrangement which exists in solids. In the next part of the lecture, we will discuss about the specific solids. We will take the examples of specific solids to understand more about the structure of the solids. To read more about this topic, you can refer to the book by S. Chand Publishing. The link to the e-book is given in the description box. You can like, subscribe and share. And do not forget to press the bell icon. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.